Sample problem 2 for work kinetic energy principle. A 250-gram ball is released from rest from a height of 10 meters and falls to the ground. Along the way, air resistance does a total of negative 3.0 joules of work on the object. Determine the speed of the ball just before it hits the ground. Okay, so back in Unit 1 in kinematics, we could find the speed of the ball just before it hits the ground, assuming a constant acceleration and no air resistance. Now we throw in a little bit of air resistance. That air resistance is going to be in the opposite direction that the ball is falling. So it's going to do some negative work on the object, and it gives you the value of that negative work of negative 3 joules. So I'm going to label that W, I guess I'll call it air. The work done by the air resistance is negative 3 joules. Okay, so I guess so air resistance is going to it's going to resist the speeding up due to gravity, so it's not going to speed up quite as much. Okay, so how do we find out the speed then? Well, we're going to apply the work kinetic energy principle, which is the net work equals to delta K. But in order to do that, I'm going to have to calculate the net work. And right now, all I have is the work done by the air resistance. Whenever you consider net work, you always have to think about what all of the forces acting on the object are. And in this case, there is gravity that's pulling it down, and then there's air resistance. Okay, so I think it's just those two, actually. So it's not going to be too long. I've already been given the work done by air resistance. So now I just have to also add the work done by gravity. So I'll just start calculating it. So WG, the work done by gravity, I'll use the work formula for this. So that's the force of gravity times the displacement times cosine of theta. The force of gravity is mg. The displacement is given as 10, so I'm just going to keep writing delta D here. So I think in problem 1, I filled in numbers early, and in problem 2, I said I would show you how to do it, just leaving things in symbols until the very end here. However, there is one number I will fill in actually, and that'll be the angle. The angle between the force of gravity and the displacement is 0 degrees. The force of gravity is straight down, the displacement is straight down, so they're in the exact same direction. And when that happens, the angle is 0 degrees, and cosine of 0 degrees is 1. And anything times 1, like multiplying by 1 doesn't change anything. So effectively, I can just cross that out of the equation there. All right, so there's my m times g times displacement is my expression for the work done by gravity. All right, if I make a list of the variables, I know my mass is 250 grams, which needs to be in kilograms actually for the SI units, so that's 0.250 kilograms. I know my G value is 9.8 newtons per kilogram. And I know my displacement has a magnitude of 10 meters. So I'm not going to concern myself with WG anymore because I'm confident that I can calculate that when I need to. Okay, so now looking over at the work energy principle. Work net equals delta K. I'm going to replace delta K with K2 minus K1. Now we're releasing this from rest. So V1 is 0. And that's another number I'll put in at the beginning actually. So yeah, I like to put zeros in. with the starting speed being 0, that means that the starting kinetic energy is also 0. So K1 disappears from that. So really, I just have work net equals K2. Now going from there, work net is the sum of the work done by, well, the individual works done by the forces. Okay, so work net is the sum of those two works, and K2 is half mv2 squared. That's the formula for kinetic energy. And the question asks us for the final speed, so I rearrange this for the speed. So that's going to be accomplished by multiplying both sides by 2. Dividing both sides by mass, and then square rooting both sides. Now, the last substitution I'll make is the work done by gravity. So this expression in yellow, I'm boxing it in yellow, that's going to go right there. Okay, so just make that the substitution. And now I believe I'm ready to fill in all the variables. So -3 for the work done by the air. Mass is 0.25 times 9.8 times 10, all divided by the mass of 0.25. Okay, put that all in the calculator. I won't do it all at once. I'm going to do the brackets first. So inside the brackets, I'm getting 21.5. Okay, now I'm going to do the rest of that. Okay, put that in the calculator, and I got 13 meters per second. Okay, I wonder if the air resistance did anything. So I'm going to use kinematics and solve for the speed without the air resistance and see if it did actually, if it actually did much. So V1 is 0. Acceleration is 9.8 meters per second squared. And the displacement is 10. These are all down. What's V2? So the kinematics formula would be V2 squared equals V1 squared plus 2AD, with V1 being 0. So then I would square root both sides. And let's see what that comes out to in the calculator. that comes out to 14. So yeah, the air resistance of -3 joules, that did -3 joules of work on the ball, managed to prevent it from getting to that 14 meters per second. It ended up only getting to 13 meters per second.